So the work I will talk about today is about improving the capabilities of language models in following instructions, and doing so using a method called activation steering. Before I get into the details of the work, just a quick word about what I'm doing, what I did so far. I'm a PhD student, and as Kirill mentioned, at ETH, and in particular, I belong to I'm part of the Language Reasoning and Education Lab that is led by Prof. Sachan. The research that I've been doing during my PhD has revolved around interpretability of language models, transformers, and some evaluation of this type of models as well, with a particular focus on tasks that involve some type of numerical or arithmetic reasoning. So I mentioned the work that we'll talk about today is about instruction following. So I would like to start by defining more precisely what I mean by instruction. So to some extent, any type of user request to a language model or a AI system can be seen as an instruction. In the scope of this work, we will use a more specific definition of the term. And in particular, what we mean by instruction is a modular constraint that can be applied on top of a base query that is semantically orthogonal to this base query. And for example, we might want to ask an LLM to summarize some text, and we might want to do that specifying a constraint that the length should be at most, for example, 2 paragraphs. This length constraint is one example of this instruction. So it's clearly it's orthogonal to, it's unrelated to what the base query is, and can be applied to many base requests. Another example can be about the inclusion or exclusion of specific word. We can ask about the generation of some content, asking the model to include a specific word or phrase. And finally, another popular type of instruction nowadays is about the format of the output. One can imagine how often a user might want to the model to generate some text according to some structure organized in some way. So I don't think I have to spend too much time motivating why this is an important capability for language models. I think everybody here had some type of experience with language models not following their instructions and having to reiterate multiple times, maybe the same constraint. For example, don't use long dashes, which seems to be happening quite often for models like ChatGPT. Definitely, this happened to people on the internet, which who complained a lot on Reddit and various OpenAI forums. So definitely, this is having models that more accurately follow and satisfy the user-specified constraint is desiderata for probably all user-facing LLM applications. And the broad questions that we target, that we address with our work is whether we can improve the capabilities of language models to adhere to this type of instruction. So to address this question, one can think of many different methods. So for example, rearranging, modifying the information in the prompt in some way. Something that's typically called prompt engineering is a method, can be a feasible way to improve the model's behavior. Lots of work has been done in this space. Another way one can think of tackling this problem is by further training the model. Obviously, most of user-facing language models are trained, fine-tuned, RLHF'd, so additionally trained in some way to be more user-friendly and to better satisfy whatever the user's request. So again, lots of work in this area to improve the model's capabilities. And finally, a more recent class of methods that was proposed to control the model's generation, so language models generation, involves intervening on the model's activations at inference time. And this is the class of method that we'll adopt for this for improving models behavior in our particular setting. So in particular, the method that we use stems from a couple of previous works. So there's this paper by Alex Turner et al. That proposed, that I believe is one of the first paper proposing intervening at inference time on the activation of a model with a vector that is computed to represent a specific concept. In this example, like sentiment with respect to a specific topic, like weddings. And by taking the difference in the model's activations with two different inputs that differ, that are similar but differ in the sentiments towards the topic of interest, one can get this representation and add it to the model activations at inference time. And in the specific case, get the model to generate text that has positive sentiment with respect to weddings, in this case, the specific topic considered. There are a couple of follow-up works that use this technique typically for high-level concepts like sentiment or formality, so different stylistic aspects of the output. Another important example that for which this technique was shown to be effective is safety, or jailbreaking. So there's this paper that got a lot of visibility by NDRDT that shows NDRDT and collaborators that shows that by intervening on the model's activations at inference time, along modifying the activation basically along a specific direction, one can get a language model that was fine-tuned to be harmless, so it was safety fine-tuned, to get to output harmful content. So basically to jailbreak the model. So now I mentioned there a couple of works show that this method can be used to steer and to control high-level stylistic aspects of the output in a language model generation. In our work, the question that we addressed is whether we can use a similar method to get the model to follow more specific constraints that are systematically verifiable. So the method that we use also consists in feeding the model pairs of inputs. So in the first step, what we want to compute a representation for a specific instruction. So we want to compute a vector that represents the specific constraint that we're interested in. For example, in this case, we might want to get the model to follow a JSON formatting when outputting some text. And what we do is we construct a data set with base queries. So, for example, list some facts about our entity. And we construct pairs by having one of the two inputs containing the instruction and one without the instruction. So we feed both inputs to the model and we store the internal model activation. So before I move forward, I want to specify more clearly what I mean by internal model activations, and specify more clearly what models we're talking about. So when I say language models, I mean transformer-based autoregressive models, for example, Gemma, Llama, Phi, and so on. And when so obviously these models consist of stacked transformer blocks, each block containing an MLP and an attention module. When these models are fed some sequence, they propagate the information from early layers to late layers, and thanks to the causal attention from early tokens to late tokens. So in this flow of information, what we're interested in capturing is the information that the model builds and and the information that is present in the model's activations at the last token of the input. So this is typically a special token like end of sequence or end of turn that signals the model that that it should start generating the output. And when I say language model activations, we store the language model activations. We always take the residual stream activations, so the output of each transformer block at the very last token of the input. And the rationale is that at this point of the model generation, the hidden states contain information not only about the next token, but also contain some higher level information about how the output is going to look like. So now back to our methodology. As I mentioned earlier, we have pairs of inputs, one containing a base request and one containing a base request plus the instruction that we care about. We feed these inputs to the model. We take the activations at the last token. We take the difference, and what we get is a vector that represents what. So the difference in the model's representation, the information that is present in one case but not in the other. And in our setting, this is the presence of the instruction. We perform this procedure multiple times by keeping the instruction the same and varying the base query. And what we do is then we average the delta vector, the difference. The rationale is that we're averaging out some information specific to the base query. This is not data angry procedure. One can get fairly clean representations with as few as 10 or 20 examples, so 10 or 20 pairs. So at this point, we obtained a representation that contains that represents the constraint that we're interested in. And then at inference time, what we do is we just add it to the model's residual stream at the same layer where we computed it. So, for example, in this case, we can ask the model, again, to list some facts about an entity without specifying any type of constraint. The model is going to output some text and possibly some numbered list, since we're asking for a list. And at inference time now, when we feed the model the same input, but we add the vector that we computed previously, we see that the model outputs, so answers the base query, but this time follows the constraint, meaning outputs some text that looks like JSON, that is formatted as JSON. So far I mentioned that we take the representation at some layer, and we take the difference between the activation at the same layer. One question here would be, what layer should we use? How is the layer selected? Also, should one perform this procedure at multiple layers at the same time, or just an individual one? So we experimented with all this. We initially experimented with one versus many layers. We realized that steering at multiple layers introduces just more noise and does not actually improve the output. And for the selection of the specific layer at which this procedure, at which we should carry out this procedure, we basically perform a small grid search in which for each instruction, we compute a specific instruction vector, and on a fraction of the data that is held out, we evaluate how frequently the steering at a specific layer gets the model to follow that instruction, and we select basically the layer that is the most effective. So the layer at which steering is the most effective, and this can vary, of course, depending on the specific instruction that we're dealing with. So now, for our experimental procedure, we consider the data from we use the data from popular data set that is typically used to evaluate the instruction following capabilities of LLMs. This dataset is called IFEVAL, instruction following evaluation. It contains many different combination of basic queries plus instruction, and all of these instruction can be systematically evaluated. So given a snippet of text, given an output that the model provides, one can systematically check whether the instruction considered is satisfied or not. And in particular, we consider three classes of instructions, or three classes of constraint. The first one is about the structure, so the format or the structure of the output, and this can be things like the JSON constraint that we saw earlier, or the output should be a bullet list, or organize the text in multiple sections, this type of constraints. Second class is of constraint is about the length, and as we saw earlier, this is fairly common type of instruction that is useful in the real world, asking the model to be either more concise, more verbose in some cases, or specifying a specific length that we would like to have the output. And finally, the third class of constraints that we consider are about specific inclusion or the exclusion of specific words. So about the first class of instructions, as I said, we use the data from IFEVAL, this data set that comes with a way to systematically check whether the model satisfies the constraint or not. And one thing that I should mention is, the score, the metric that we will use to evaluate our method and the various baseline is basically this binary accuracy value that is given. This can be computed systematically for each instruction, for each input, basically. So so it's 1 or 0, depending on whether the model followed the instruction or not, and we just average this value over all the evaluation set. And another thing that I would like to mention is that this metric takes into account only the instruction, and actually not how faithfully the model answers the actual base query. So in the case we saw before, the facts about the entity that we requested. To take that into account, we construct a pipeline that just verifies that when we perform steering, the quality of the output, the quality of so how well the model addresses the base query does not change, does not degrade. And I'm happy to elaborate more on this later. But back to the results about instruction following. So the first setting that we consider, the first thing that we do is we compute this instruction following metric when we provide a model just base queries without an instruction. So obviously in this case, the expected accuracy score should be 0, because there's no reason why the model should follow an instruction if this instruction is not mentioned in the input. In practice, this value is around 10-12%, and it's because in some cases the model's output happens to satisfy what the constraint would be. So these are cases like don't include any commas in the output, for example. So in some cases the model might actually answer the query without using commas, and in that case would count as instruction satisfied. So this serves as a baseline metric. What we evaluate next is the same accuracy score, but again, when we do not provide a specific instruction, when we don't provide any instruction in the input, but we steer for a specific instruction. And after that, we take the model's output and evaluate whether the constraint was followed or not. And what we see in this case is a significant increase in the instruction following accuracy. And what this means is that, again, even if we don't specifically, so the input does not contain any information about how we might want the output to look like, performing steering, so adding a vector that represents the constraint to the model's activation, gets the model to satisfy that constraint. So the model's output satisfied the desiderata. Now, a follow-up question to this would be, can we perform this procedure when we have already provided the instruction to the model as a natural language in the input? So in this second, actually third setting, we construct inputs with base query plus instructions. And again, we feed them to the model, we compute the accuracy. In this case, obviously, the value is going to be larger. It's around 68, 70%. And again, we perform the same procedure. So same input, query plus instruction, plus steering for the instruction specified in the input. And in this case, interestingly, we see, again, an increase in the instruction following accuracy. And what this is telling us is that there are cases in which the model, which, by the way, for these specific numbers is phi3. In the paper, we have carried out other experiments with Gemma and Mistral. But there are cases in which the model does not follow the instruction, even though it's, the model is asked to do that. And this happens roughly 30-35% of the time. And by performing steering, one can basically correct some of these failures. And one way to see this is kind of a reiteration of the signal that represents the instruction that basically is reinforced when one performs steering. So these were the results for this first class of instructions that we considered. The second set of constraints is about the length of the output. And what we do, so for this class of constraints, we carried out a couple of different experiments. Here, I would like to focus on one of these. And in this experiment, what we do is we compute a representation, not for a specific length constraint, like 2 sentences or 3 sentences or 1 paragraph and so on, but we capture a more general concept of conciseness. And we do this by performing the same procedure in which, again, we have pairs of inputs, one without instruction and one with instructions that are like the output should be short, the output should not be too long, be concise, and so on. Again, we feed the model pairs of this input. We store the representations, take and average their difference over multiple inputs, over multiple pairs, and then we experiment with adding this conciseness vector to the model's representation, and in particular, we experiment modulating its strength. So we start by asking the model to generate in some preliminary experiments, we ask the model to generate, we give the model a very open-ended generation query, like write a poem about a topic. The model is going to be very verbose, and in this case, answers with multiple paragraphs. And then we, again, perform the same, and we steer, so we add our conciseness vector to the model's representation, and we multiply this vector by a weight. And by increasing the weight, we notice that the outputs start to be shorter in this case, two paragraphs, and then we increase the weight even more, and then the model output just 2 lines. Then this is one example that we actually obtained by playing around with the model in some very preliminary experiments. We quantified this, and we quantified this more rigorously. And what we did is we measured, for many different queries, we measured the length in terms of number of words of the output of the model, and plotted distributions when we perform steering with different weights. So in this histogram, the different color represents different weights, and the baseline distribution is for weight equals 0. In this case, you can see how the distribution. So there's a lot of variance in the length of the output. Depending on the query, the model can be very verbose or can be concise in some cases. But when we increase this weight, which is a scalar that we use to multiply our steering vector with, we start to see that the distribution of the output length gets more and more squeezed towards low values. And what this is telling us is that we can, in cases in which the constraint that we are interested in as this continuous nature, for example, like the length of the output is one such case, we can continuously modulate this property of the output by, again, intervening on the model's inference time with different steering weight. So this is one of the examples, one of the experiments that we carried out for this type of constraints about the length. And finally, the last class of instruction that we'd consider is about the inclusion or the exclusion of specific words or phrases. For example, we can ask the model to rephrase a particular sentence without reusing a specific term. This is one of such examples. As before, we again evaluate the model and our steering procedure in 2 settings. One in which there's no mention of the constraint in the input, and one in which the constraint is specified in the input. So in this case, we feed the model again just the base query, so the first part of the input, and we compare the frequency at which this constraint is satisfied versus the same quantity, but when steering is performed. So for phi and gamma, in this case, the baseline extraction following accuracy is around 60%, which means 60% of the time the model by default does not include a specific word. And then when we steer, so we compute a vector representation that is specific to the word, and in this case, instead of adding it to the model's representation, we actually subtract it to remove the component of the word that represents the component of the residual stream of the model's activation that is about the specific word that we'd like to exclude. When we do that, we see that the model more frequently does not include the word in the output. And as before, we then repeat the same experiment when we explicitly ask, but this time we explicitly ask the model to exclude a specific word. And again, in this case, the baseline accuracy, which is the solid colored column, is of course higher. But also in this case, when we perform steering, we observe an increase, basically an improvement in the performance, an increase in the number of times that the model actually follows the constraint and does not include the specific word. These results are about word exclusion. We perform a similar experiment for word inclusion. And again, in both settings, the results are similar, where we observe an improvement in both cases, basically. So this was the third class of instructions that we considered. So then while we were working on this, there were a couple of follow-up questions, a couple of questions that emerged. And we experimented, we ran some experiments to address. So one of these is, can we perform the steering procedure for multiple instruction at the same time? One can think of many settings in which a user in the real world might be interested in adding, like, or specifying basically multiple constraints when interacting with a language model. And to simulate the scenario, we constructed a data set of Bayes queries, and we combined a constraint about the formats of basically first class of the first class of instruction that we saw earlier, and a length constraint. And the procedure that we follow here is basically the same as before, except we applied twice. We carried out twice. And as I mentioned at the beginning, the layers. So for each instruction, we compute a specific vector, and for that specific vector, we identify the optimal layer to perform steering at, and we just perform this procedure twice. And one, adding to the model's activation the vector representing the format constraint, in the second case, the length constraint. And what we observe is an improvement along both axes. So in this plot, the two axes represent the two accuracy values for the two constraints. The 2 points at the beginning of the arrow, so the lighter points represent the baseline accuracies in the two cases, with instruction in the input and without instruction in the input. And the points, the solid, the darker points where the arrows are pointing are the accuracy values after steering. So what we observe is, again, in both cases, in both settings, with and without instructions in the input, performing steering increases the number of times the model follows the instruction, and this happens for both constraints. And finally, another question that popped up that we thought of while working on this is about the transferability of these representations. So we started wondering how, whether one can transfer steering vectors for a specific constraint from one model to another. Obviously, some different models that are trained on different data and on shared architecture have representation spaces that are completely different. So in such cases, one would need to learn some kind of mapping from one space to the other. And this is actually something that we did in some follow-up work. In this work, what we did is we experimented with two versions of the same Bayes model. So basically, Bayes model and an instruction-tuned version of the same model. And in practice, we use the Gemma models that come in both versions. And what we did is we computed the steering vectors, so the instruction vectors, on the instruction-tuned version of Gemma. And then we used it to steer the Bayes version of the model. And we observed that this works. And in particular, this actually seems, in some cases, works better than steering the Bayes model with the vectors computed on the Bayes model. And this was a mildly surprising result. So on one end, this might be expected. So the reason why, the rationale behind this result is that, so one thing is that the representation space between instruction-tuned models and the equivalent Bayes models, the corresponding Bayes models, do not differ that much. So there's been a couple of works that showed how the weights of models that undergo basically post-training, RLHF, and any kind of this kind of post-training, the weights don't differ that much, don't change that much. And this is one of the reasons why we experimented. We ran this experiment because there was some hypothesis that this might work. And the reason behind an explanation behind the higher accuracy scores and better performance obtained when steering, basically when performing this cross-model steering, is that instruction-tuned models are obviously trained to be better at following instructions. And probably one of the reasons why this is the case is these models are better at translating the natural language, specifying the instruction in the input to representation that then gets translated in a specific feature, specific characteristic of the output. So there are cases in which the base models fail completely at capturing the instruction specified in the input. And by computing an instruction vector and steering vector on the instruction tuned version of the model, one is able to get basically a richer, like better representation for the desired constraint. And that the representation is still meaningful in the representation space of the base model. And so the conclusion is that between base models and instruction tuned models, there's this transferability that can be possible, that is possible, and on top of that, in some cases, we observe that performing this cross model steering can actually be more effective. And this is interesting because it opens for some possibilities of, for example, fine-tuning the same base model on different data or different tasks, and then transferring representations based on the best model, like the model that is best at doing or capturing a specific aspect of the input. So to recap what we talked about today is that in this work we showed that it's possible to compute meaningful vector representations of instructions, so user-specified instruction and constraints in the input. And one can do that simply by taking the difference in the model, in the model's activations onto between two inputs that differ in the present of the instruction that we're interested in. Then this representation can be used at inference time to control the model's generation and improve the model's adherence to different type of constraints. So constraints about the format of the output, its length, and the exclusion or exclusion of specific words. The improvements that we observe by steering, performing the steering procedure, appear both, so not only when the model is not provided the instruction, and in this case, basically, they can be seen as a replacement for the natural language, for the tokens in the input that specify the constraint, but also when the constraint is actually already specified. And in this case, this can be seen as kind of a reinforcement of the signal coming from the, or representing the constraint. And in some follow-up experiments, we showed that it's possible to perform the steering procedure for two instructions at the same time and get improvements along both axes for both instructions. And finally, we just saw the between instruction-tuned models and base models, it's possible to transfer the representation and perform this kind of cross-model steering. I would like to conclude, by thanking my collaborators. I worked on this as part of my internship at Microsoft Research last year. We were very happy that the paper, that stemmed from this work, got accepted. iClear, we presented a couple of months ago in Singapore. And yeah, with this, I'd like to conclude. I'm very happy to take any question and discuss any follow-up or any thought that you have.